Myself, Sheethal P., Assistant Professor, Department of Artificial Intelligence and Machine Learning. Today, I am going to explain about machine learning techniques. I am going to explain about what is machine learning, what are the techniques used in machine learning. Machine learning is a data analytics technique that teaches computers to do what comes naturally to humans and animals, learn from experience. Machine learning algorithms use computational methods to directly learn from data without relying on a predetermined equation as a model. As the number of samples available for learning increases, the algorithm adapts to improve performance. Deep learning is a special form of machine learning. How does machine learning work? Machine learning uses two techniques, supervised learning and unsupervised learning. Supervised learning, which trains a model on non-output input and output data to predict future outputs, and unsupervised learning, which uses hidden patterns or internal structures in the input data. Supervised learning in detail. Supervised machine learning creates a model that makes predictions based on evidence in the presence of uncertainty. A supervised learning algorithm takes a non-set of input data and non-responses to the data, that means output, and trains a model to generate reasonable predictions for the response to the new data. Use supervised learning if you have non-data for the output you are trying to estimate. Supervised learning uses classification and regression techniques to develop machine learning models. Classification models classify the input data. Classification techniques predict discrete responses. For example, the email is genuine or spam, or the tumor is cancerous or benign. Typical applications include medical imaging, speech recognition, and credit scoring. Use taxonomy if your data can be tagged, classified, or divided into specific groups or classes. Common algorithms for performing classification include support vector machines, that means SVMs, boosted and backed decision trees, k-nearest neighbors, naive bias, discriminant analysis, logistic regression, and neural networks. Regression techniques predict continuous responses, for example, changes in temperature or fluctuations in electricity demand. Typical applications include power load forecasting and algorithmic trading. Various common regression techniques are used in this. Some of them are linear, non-linear models, regularization, stepwise regression, boosted and backed decision trees, neural networks, adaptive neuro-fuzzy learning. Using supervised learning to predict heart attacks. Physicians want to predict whether someone will have a heart attack within a year. They have data on previous patients, including age, weight, height, and blood pressure. They know if various patients had a heart attack within a year. So the problem is to combine existing data into a model that can predict whether a new person will have a heart attack within a year. Next, we are going to see about what is unsupervised learning. Unsupervised learning detects hidden patterns or internal structures in unsupervised learning data. It is used to eliminate data sets containing input data without labeled responses. Clustering is a common unsupervised learning technique. It is used for exploratory data analysis to find hidden patterns and clusters in the data. Applications for cluster analysis include gene sequence analysis, market research, and commodity identification. For example, if a cell phone company wants to optimize the locations where they build towers, they can use machine learning to predict how many people their towers are based on. A phone can only talk to one tower at a time, so the team uses clustering algorithms to design the good placement of cell towers to optimize signal reception for their groups or groups of customers. Common algorithms used for performing clustering are k-means and k-medoids, hierarchical clustering, Gaussian mixture models, hidden Markov models, self-organizing maps, fuzzy C-means clustering, subtractive clustering. 10 methods that gives a foundation you can build on to improve your machine learning knowledge and skills are regression, classification, clustering, dimensionality reduction, ensemble methods, neural nets and deep learning, transfer learning, reinforcement learning, natural language processing, word embedding. Now we can see what is regression. Regression methods falls under the category of supervised machine learning. They help predict or interpret a particular numerical value based on prior data, such as predicting an asset's price based on past pricing data for similar properties. The simplest method is linear regression, where we use the mathematical equation of the line y equal to m into x plus b to model the data set. We train a linear regression model with multiple data pairs, that is x and y, by computing the position and slope of a line that minimizes the total distance between all data points and the line. In other words, we calculate the slope m and the y-intercept b for a line that best approximates the observations in the data. Regression techniques run the gamut from simple linear regression to complex, that means regular linear regression, polynomial regression, decision trees, random forest regression and neural networks. Next is classification. In other class of supervised machine learning, classification methods predict or explain a class value. For example, they can help predict whether an online customer will purchase a product. Output can be yes or no, buyer or no buyer. But the methods of classification are not limited to two classes. For example, a classification method can help assess whether a given image contains a car or a truck. The simplest classification algorithm is logistic regression, which sounds like a regression method, but it is not. Logistic regression estimates the probability of occurrence of an event based on one or more inputs. We fall into untrained machine learning with clustering methods because they aim to group observations with similar characteristics. Clustering methods do not use the output information for training, but instead let the algorithm define the output. In clustering methods, we can only use visualization to observe the quality of the solution. The most popular clustering method is k-means, where k represents the number of clusters selected by the user. Randomly chooses k centers within the data, assigns each data point closest to the randomly generated centers. Next one is dimensionality reduction. We use dimensionality reduction to remove the least important information, sometimes unnecessary columns from the dataset. For example, images may consist of thousands of pixels which are unimportant to your analysis. Or when testing microchips, within the manufacturing process, you may have thousands of measurements and tests applied to each chip, many of which provide redundant information. In these cases, you need a dimensionality reduction algorithm to make the dataset manageable. The most popular dimensionality reduction method is principal component analysis, which reduces the dimensionality of the feature space by finding new vectors that maximize the linear variance of the data. You can also measure the extent of information loss and adjust accordingly. When the linear correlations of the data are strong, principal component analysis can dramatically reduce the dimension of the data without losing too much information. Another popular method is T-stochastic naive embedding, which minimizes non-linear dimensions. People usually use this method for data visualization, but you can also use it for machine learning tasks such as feature space reduction and clustering, to mention a few. Next one is ensemble methods. Imagine that you have decided to build a bicycle because you are not happy with the options available in stores and online. Once you have assembled these great parts, the resulting bike will outlast all other options. Each model uses the same idea of combining multiple predictive models. That means supervised machine learning to obtain higher quality predictions than the model. For example, the random forest algorithm is an ensemble method that combines multiple decision trees trained with different samples from a dataset. As a result, the quality of predictions of a random forest exceeds the quality of predictions predicted with a single decision tree. Think about the ways to reduce the variance and bias of the single machine learning model. By combining the two models, the quality of the predictions becomes balanced. With another model, the relative accuracy may be reversed. It is important because any given model may be accurate under some conditions but may be inaccurate under other conditions. The most popular ensemble algorithms are random forest, XGBoost and LightGBM. Next one is neural networks and deep learning. Unlike linear and logistic regression, which is considered linear models, neural networks aim to capture nonlinear patterns in data by adding layers of parameters to the model. The simple neural net has three inputs in an input layer, hidden layer, and 5 parameters and an output layer. Neural network with a hidden layer. The neural network structure is flexible enough to construct our famous linear and logistic regression. The term deep learning comes from a neural network with many hidden layers and encompasses a variety of architectures. Deep learning, a neural network with multiple hidden layers. Deep learning techniques require a lot of data and computation power for best performance, as this method is self-tuning many parameters with vast architectures. It quickly becomes clear why deep learning practitioners need powerful computers with GPUs, that means graphical processing units. In particular, deep learning techniques have been extremely successful in vision, image classification, text, audio and video. The most common software packages for deep learning are TensorFlow and PyTorch. Next one is transfer learning. Now we are looking into what is transfer learning. Transfer learning refers to reusing part of an already trained neural network and adapting it to a new but similar task. Specifically, once you train a neural network using the data for a task, you can move a fraction of the trained layers and combine them with some new layers that you can use for the new task. The new neural network can learn and adapt quickly to a new task by adding a few layers. The main advantage of transfer learning is that you need fewer data to train a neural network, which is especially important because training for deep learning algorithms is expensive, both in terms of time and money. Of course, it isn't easy to find enough labeled data for training. Transfer learning has become more and more popular, and there are many concrete pre-trained models now available for common deep learning tasks such as image and text classification. Next one is natural language processing. NLP is not a machine learning method but a widely used technique for preparing text for machine learning. Think of many text documents in different formats, that means Word, online blog, like that. Most of these text documents will be full of typos, missing errors and other words that need to be filtered out. At the moment, the most popular package for processing text is NLTK, that means Natural Language Toolkit. The easiest way to map text to a numerical representation is to count the frequency of each word in each text document. Think of a matrix of integers where each row represents a text document and each column represents a word. This metric representation of the term frequency is usually called the term frequency matrix, that means TFM. We can create a more popular metric representation of a text document by dividing each entry on the matrix by the weighting of the how important each word is in the entire corpus of documents. We call this method term frequency inverse document frequency, TF-IDF, and it generally works better for machine learning tasks. The last one is word embedding. TFM and TFIDF are numerical representation of text documents that consider only frequency and weighted frequencies to represent text documents. In contrast, word embedding can capture the context of a word in a document. As with word context, embeddings can measure similarity between words, allowing us to perform arithmetic with words. Word2VEC is a neural net based method that maps words in a corpus to a numerical vector. We can then use these vectors to find synonyms, perform arithmetic operations with words, or represent text documents by taking the mean of all word vectors in the document. For example, we use a sufficiently large corpus of text documents to estimate word embeddings. Studying these methods thoroughly and fully understanding the basics of each can serve as a solid starting point for further study of more advanced algorithms and methods. There is no best way or one size fits all. Finding the right algorithm is partially just trial and error. Even highly experienced data scientists can't tell whether an algorithm will work without trying it out. But algorithmic selection also depends on the size and type of data you are working with, the insights you want to derive from the data, and how those insights will be used. Thank you.